Hi everyone, my name is Sydney Sanchez and this is my final project for this course. The project is titled Ensemble Model for Leukemia Subtype Classification. Some table of contents of what I have here for you guys today is some brief introduction, exploring the data, how I handled missing values, how I prepared the data, and the different machine learning models I used and their metrics, as well as the ensemble models I ran and the challenges I faced during this project. Some brief introduction. I found this data set online. It was published in Science in 1999, so it is a widely used data set. It's the Gola et al. Leukemia data set. It is a gene expression data using microarrays to classify acute lymphoblastic leukemia, ALL, and acute myeloid leukemia, AML, in 72 patients. So the goal for me using this data was to predict whether the patient has ALL or AML based on their gene expression data. So this is a categorical project. And I did make an ensemble model, which includes logistic regression, SVM, and random forest. When it came to exploring the data, I wanted to get a brief view of what was present. So there were 7,130 genes or features across 72 samples or observations. That is a lot of data across a few amount of samples. So there is fear of some overfitting here. It contained 47 ALL samples and 25 AML samples. And I took a brief look of what I could see. There is a PCA plot on the left here, which I distinguished the ALL and AML classes. As you can see, there is some slight distinction between the two classes if you view the PCA, obviously with outliers included, but there is some distinction there. And I also looked at this volcano plot that compares the AML and ALL differential expression. So the red values on the right side are upregulated in AML and compared to ALL, and the values on the left side are downregulated in AML compared to ALL, or like ALL is upregulated in those genes. So there are clear distinctions of genes that could differentiate between the two significantly. And when it came to missing values, this data set didn't contain any missing values, so I randomly removed 100 values and imputed them with column-wise mean. And that's what I used downstream in the data. I also wanted to explore some more of like scaling and outliers. As you can see, the box plot on the left shows the 20 top, like the top 20 most variable genes, and they're mostly scaled along the median here of like the zero value, which shows that they're all right. I knew they were logged to transform and going into it, so I knew I didn't have to do any further transformation. And then the box plot here are the top 20 genes with expression and outliers highlighted in red. As you can see, there are plenty of outliers, but since this is gene expression data, I have chose to not remove them or not capping the outliers because that could de-signify the importance of the expression of that gene. Sometimes it is very common to have very highly or underexpressed genes like I showed you in the volcano plot previously, and it is very normal to have that for these data set, and it does show the influence that the data has. For data preparation, I encoded the class column to binary, so ALL is 0 and AML is 1. Some of the algorithms required a binary class to do that. And then I selected the top 100 variable genes to reduce overfitting. Since there were 7,000 roughly genes, it was too much against just 72 samples, so I wanted to bring that down. So I chose the ones that were the most significantly variable between the two. I Z-score scaled the features, which was necessary for logistic regression and SVM. It wasn't necessary for random forest, but it doesn't negatively affect it either, so I just used the same scaled features for that. I checked the highly correlated pairs, and there were a handful, so I removed some of the genes that were present in some of those pairs to try to reduce multicollinearity. And the final data set I had using downstream was 77 genes across those same 72 patients. And I can show briefly the code that I ran for data prep. So here we are in my R console where I have the code chunk of the data preparation steps. So I did make a copy of the original data. I did the encoding class here, the binary one. And then here, this is where I got the top 100 most variable features by computing variance and got those top genes there. Then I subset that data and also scaled them, the z-score scaled. And then I combined those. But then I took a look at the correlation matrix and did find that there were highly correlated pairs. And from there, I removed those based off of a cutoff, filtered those genes, and then had this final prepared data frame that was filtered to use downstream. So let me go back to my slides. So these are the different machine learning models I used. I use logistic regression because it's a simple baseline for binary classification. It does capture feature selection and linear trends. And then I used SVM because it performs well when there's a small number of samples like I have in this data set to help reduce overfitting. And it also does capture nonlinear relationships. And then using a tree-based model, random forest does handle nonlinear relationships and interactions, which it does with ranking. So I wanted to have a variety of models that could hopefully improve on each other's flaws. And then I did assess the performance based off of accuracy, precision, recall, F1 score, ROC, AUC, and a confusion matrix. So this is basically how some of the individual models performed. I will show in the code how I ran the ensemble later on, but this is just the individual ones. Here, this is the lasso versus ridge logistic regression. I wasn't sure of which method to use, so I ran both to identify which one I wanted to use in the ensemble. Here, the lasso outperformed the ridge method, and that's what I decided to go through. It did have a slightly lower AUC, but it's not enough to compensate for like the differences here in accuracy and precision and F1 score. So that's why I stuck with lasso. And then the SVM model, I ran the three different methods, linear, polynomial, and RBF, to try to see which one performed best. They all performed very similarly. They all had the same accuracy, precision, recall, F1 score. There's only a slight difference of AUC, so just because of that, it is very slight and minuscule, but I decided to proceed with the SVM linear method for the ensemble. And then continuing with my random forest model, this is one of the models that kind of challenged me the most because I was trying to bring up the accuracy. When I ran just the base model, it had an 81% accuracy, 75% precision. Recall was good, and F1 score was all right, and AUC was all right, but I didn't compare to SVM and linear regression. So I wanted to like bring it up a little bit more. And I tuned using a tuning grid. So I added different values of M-tree values to try. And then from there, it would pick the best value that performs the best ROC wise. And then I added increased number of trees. So I think I did 1,000 trees. And that did help a good amount. It did improve the accuracy to around 90%, improved precision, recall stayed the same, so that was good. And it improved F1 score and stuck with the same AUC. So I was happy with that performance there, and I stuck with this tuned random forest for the ensembles as well. So when it came to the ensemble, I struggled a lot. I initially started with a majority voting ensemble, and as you can see here, this is a table that I have of all the methods individually and then the ensemble majority or stacking. Here the ensemble performed the same, and it did have better precision, but it did lack recall, so it kind of had to excuse me, it had to um kind of compensate for that. And then the F1 score was kind of not as well, and the AUC score dropped. So I wasn't too like happy with that. So that's when I proceeded and tried a stacking method, which was a slightly more complicated method. I hadn't run it before, so I had to really dig in deep and learn with this one. So the accuracy was still the same. Precision balanced down a bit compared to the majority, but at least recall was good and it wasn't as low as how recall was for ensemble. The F1 score improved and was similar across the other individual models. The AUC score dropped a little bit, but that's expected when trying to make up for lack of precision and like recall. So overall, I chose to go with the stacking ensemble because I do am a firm believer that using a balanced overall integrating multiple like base learners will achieve a more like reliable classification. So that's what I went with. But if you look at all of them, overall the SVM did perform the best by small metrics, but um, yeah, that's something I did notice. And here I can show you the code where I ran the both ensemble models. So this is where I ran the majority vote ensemble model. And again, as we know, the vote basically each model votes on which class they want to predict that sample to be. And then whichever one has a majority will take on that in the final conclusion. So since there were only three models, I didn't have to deal with like a tiebreaker or anything. So it was either 2-1 or 3-0. And I did that, and when I run it, let's see here, I ran and got all the metrics with that as well, and that's when I got this performance here. As you can see, like I showed earlier, it didn't perform too well compared to just like one of the individual SVM models, so I wanted to try something else. And that's when I moved on to the stacking ensemble model. And this does have a deeper complex level of the meta learner, so it is a little bit more complicated. A flaw is that this data set doesn't have that many samples, so it could cause some trouble there. But I did use a K-base folded classification, like five-fold CV, so hopefully that did help with the correct list package and stuff. And that was my intention there. My apologies. Here we are again with the stacking ensemble model, and here I am running it. Um, Here I ran the model and did the stacked ensemble there with the same methods I had used before and did metrics as well. And here's that table of the stacked ensemble. As I had shown previously, it did perform very similar, just had slightly higher or had slightly higher precision with benefit of recall, and the AUC had dropped slightly. Let me go back to my slides. And then going back to the original data that I had removed the missing values and imputed them, I did want to run that stacked ensemble on that data without having imputed those missing values. And I did get a higher accuracy, higher precision recall, overall higher performance. I wasn't entirely sure if this was due to the missing values. Since there were only 100 missing values, I don't think it would have um, necessarily impacted them instead unless there were like some expression values that were highly differential and did have high importance in predicting the data. So that is a possibility. I also believe because I did split or resplit the data again to analyze for that, it's possible that a different subset of the training and testing sets led to higher results. But I think it just goes to show that the model does perform well, even when applied to like a different data set. Some challenges that I faced, there were a lot, but overall, I think just because of the small data set, leading to limited learning power, just having 72 samples is tough, especially because gene expression data is over thousands of genes, so that does like introduce a lot of overfitting. And then I did face some low model diversity. I was expecting some of the base models to have higher differences amongst the three, but they all had very similar like metrics across the board. So it was just difficult to have some of them compensate for each other when they just at the end of the day ended up kind of averaging out. Um, the majority vote didn't go in my favor, but I did try stacking as another method, but it seemed like the majority vote kind of boosted precision but hurt recall. And it does sometimes go to show that combining models doesn't always lead to a balance improvement. Like SVM did outperform the majority vote ensemble, but it could have possibly been tweaked some more to have it perform even better. Um, and then with stacking, again, it kind of does need more data when you're dealing with a meta learner and having to deal with two layers of data to make predictions. Since it's a small data set, that does make it difficult, but it was very interesting to learn how to do that as well. I want to say thank you, and here is the reference to the data that I used and their paper. Thank you, everyone.